Log on, tune in, find out. Another good idea from Cambridge.
Ludmil for giving us a kind of mini course. He's going to give 2 lectures at different times. Be aware of the times. The second one's at something like 2:30. 2 o'clock. 2 o'clock. Yes, 2 o'clock. So you'll all be here, just not me. No, forgotten. And he's going to talk about spectra and gaps and categories.
Thank you very much for giving me the opportunity to speak here. I was told by Koncevich that no event is meaningful if there is at least one bad talk. So now we are in a position to make this event doubly meaningful.
We've had plenty of bad talks.
In any case, my plan was as follows. So first, I'll give some definitions. And then consider some examples. Then I'll possibly discuss some applications to algebraic geometry. And then the fourth part, which is basically the second talk, is to explain actually where all these things are coming from, meaning they are natural continuation of some previous work that I have done, and basically it will be how to compute. So I have been always trying to look at some sequence of numbers and in a way to try to guess what algebraic variety, what smooth projective variety one can actually associate it with this sequence. And so one of these sequences 4, 5, 6, 7 and so on until 27, and then we have a gap here, and then we go to 30. Or another sequence where we miss here 29. And so the first part, at least, of our discussion will be to give some meaningful geometric interpretation of this sequence. And so let me start with some definitions. So for me, it will be a triangulated category. Most of the time, dB of x for x smooth projective. Or Fukaya category of a symplectic manifold Y. And so if I have G an object in tau, I'll say that G0 is the minimal subcategory containing G closed under isomorphisms shift finite direct sums and summands. So now inductively we can define Gn to be the subcategory consisting of objects B such that B is contained in a distinguished exact triangle of the following form, where y belongs to G0 and x belongs to Gn minus 1. So now if there exists n such that Gn is equal to tau, we will say that G is a strong generator and otherwise so we'll say that G is a strong generator, and let's denote by T of G the number, so the minimal n, such that the Gn is equal to tau. Now, if such n does not exist, we will say that T of G is equal to infinity. And now we'll denote by Orlov spectrum of the set of all generation times, in a way ordered in increasing manner. So this set, of course, could be unbounded, but there are some bounds which have been established, and I'll briefly discuss them in this talk. So in any case,
sorry, question?
Yes.
For the infinity case, do you still require that G generates so that any object can be cut at some time that is bound, or?
Well, I mean, so in this case, G is a generator, but not a strong one.
Okay. And if G just doesn't generate, then do you still put T equals to infinity? Or do you just not have it?
Not consider it.
Okay.
So the spectrum of the category tau, in other words, consists of several numbers, which are the so-called generation times of the strong generator. So this notion is very much connected with the previous works of Bondo and van den Berg, and then of Rouquier. So in particular, the Rouquier studied the smallest number in this spectrum, and so the minimum in the spectrum of tau, it was introduced by Rouquier, and he called this a dimension of the category tau, and there was a conjecture made by him and later specialized in the case of dB of smooth projective variety, that if X is smooth projective, and so we consider tau to be the category dB of X, then conjecture by Orlov states that the dimension of tau is equal to dimension of X. So X is over the complex number. So later on it was proven that by Orlov that if X is smooth projective curve, then the dimension of dB of X is equal to 1. Okay, so this is more or less when I actually started looking at this, and so what I'll present here is basically what I've learned from my collaborators, Favero and Ballard, and also Kerr, but maybe give you a little bit different point of view on these kinds of things. So let's consider some examples which we will try to draw some conclusions from. So the first example, which we will return to in the second talk, is the category dBFE, where E is an elliptic curve.
Is conjecture even known for projective space?
For P2 and P3, yes. Well, for, I'm sorry, actually I want to say that for P2 and P3 it's known, and actually we do know more, and I'll discuss it briefly now. And yeah, I mean, the point of the talk is that maybe there is a method which would allow you to compute more, but it still needs some development. So, but in the case of elliptic curve, so the following theorem by Bard, Vero and myself states that the spectrum of tau in this case consists of the following numbers. And so let me do the following table. So if the generation time is equal to 1, one possible generator is O of P plus, O of 3P plus O of minus 3P. So O is the structure shift associated with this elliptic curve. For 2, the generator that generates this category in 2 steps is O of 3P plus O. Basically what we are doing is we look at all these operations that participate here, and so we look how quickly we can get the category by applying G several times. But so we look at all these possible operations, and so all these things are actually forgotten, and the only thing that matters is the triangles. This is what we count. This is how we look at this category. And so in 3 steps, namely with all these operations and at most 3 triangles included, we get O of 2P plus O. So this is the generator that generates in so many in 3 steps, and the one that generates in 4 steps is O of P plus O. So P is arbitrary quantity. So as I said, I'll return to this statement later in my second talk. Well, we'll see. We'll look at it from different perspectives. So let me give 2 more examples. Which first are to give you some more feeling about this, and then to build up a little bit in order to be able to approach some questions of birational geometry. So we stay with dB for now, but we'll look at dB of P2. And then in this particular case, again, we have the following table. So the spectrum of this category consists of 2, 3, and 4, and the generators with this generation times are so again always the structure sheet. The one that generates in 3 steps is the following object. So O of L here is the structure, sorry, the skyscraper shift associated with any line in P2. And the one that generates in 4 steps is O plus O of L plus O of, I'm sorry, yes, that's correct. Where L is, actually, let me make a small change here, sorry about that. Where P is a point. And I'm not saying that there are no other generators which generates in 2 or 3 or 4 steps, namely there are 2, 3, and 4 triangles. In fact, there will be many, and in some cases infinitely many of them. And you can try to put more structure on this in case there are finitely many generators, to ask how many different generators generate in so many steps, and so you can introduce further more refined notions of double, triple spectrum, and so on and so on. But for now, let's stay with this thing here.
And won't there always be infinitely many? I'm a little confused. Can you take any direct sum of the previous ones?
Yeah, but so at the beginning, yes, but when you look at towards the end, they tend to be only finitely many. In fact, the ones that generate in the slowest possible way seem to be very, very, because if you add them, obviously you move further.
Yeah.
So these are the interesting ones.
You can certainly add it to itself.
Yeah, but then you're going to move above. Yeah, but so this is part of the operation. Remember, the sums is considered as a part of the operation. So the question is, I mean, what you are going to.
So would be 3, and I guess that the kind of highest time generator would be O1 plus surface curve and a point.
So, I mean, that's a good observation that indeed, in the case of Pn, the full flock gives you the slowest generator. So we will get to this eventually.
Does the Bondal-Vandenberg result tells you this dimension is always less than the dimension of x or something?
Root here.
I mean,
root here.
yeah.
I see.
So the dimension of x, it gives you a bound from below.
Or from below?
Yeah. Right?
Dimension of t is greater than or equal dimension of x.
Yes.
Greater.
Yes. The dimension of x is lower bound. So let's look at just one more example. So just to confirm what Timothy was suggesting. So just consider the case of P3. And similarly, so we have and the corresponding generators are where H of H is the skyscraper shift over plane in P2, plane in P3. Then O plus O of 2 plus O of H plus O of OH or L, where this is skyscraper shift forward plane and line, generates in 5 steps. And then the slowest generator, one of the slowest generators, is O of 1 plus these 3 skyscraper shifts over a plane, line, and a point. So now this result suggests the following conjecture. That in the case, well, it's much more general, but let's restrict ourselves to the category GBFX, X smooth projective. Then the spectrum of this category is between the dimension of X and the sum of homology of X plus dimension of X minus 1.
Sorry, H, sum of what?
Of the homology of beta numbers. And so, I mean, for people who are more curious, then this is basically just part of the conjecture that what we have here is the sum of the Hochschild homology of the category plus the dimension of the category minus 1. And in this particular case, this is what we are getting.
I thought it's not greater than 2-dimensional X minus 1.
Sorry?
Should have been 2-dimensional X.
No, not that. If we, the upper bound, if we change it for 2-dimensional X minus 1, 2 times dimensional X minus 1.
Then it would fail to be electric current.
No, I mean, that's too small. I mean, so let's try. So for the case of the elliptic curve, so what we have, the sum of the homology is equal to 4. And then we have the dimension plus 1 minus 1, and then it's between the dimensions, so indeed. We have this. And similarly for P2, so now, I'm not saying that any number in this interval is actually attained. So it could be that there are numbers which we are missing. And so this is the second notion that I want to discuss, and this is the notion of a gap with the spectrum of the category.
It's about the upper bound. Is it always 3?
Yes, that's what it's a conjecture. But
Might be small.
I mean, in this examples, yes. But I mean, so
So did you say that Ruppier's conjecture was only known for P2 and P3?
I mean, for P2 and P3, we actually know more. We know the whole spectrum. Ruppier's conjecture is just that the smallest element in the spectrum is equal to the dimension.
For P4, we don't even know that O plus O1.
Yeah, I haven't looked at before, but I don't expect that it's so much different.
I mean, the first generator X is the same for Pn.
Yeah. But I mean, I have for Pn, obviously the result should be like that. Okay. So now, as I said, there could be actually some numbers in between which are missing, and so I'll spend a little bit of time talking about this. So let's consider a following category. So the category of so let's consider a category of singularities. dB sync of the function z to the 8th. So let me just remind you that the derived category of singularities, so I'm sure that is defined as always as follows. So you take quasi-projective variety y and a function on it f, and this is giving you a proper map from y to f to c, and then you consider the singular fibers of this, and this is just a direct sum of the derived categories of the singular fibers. Modulo the subcategory of perfect complexes of this singular fiber. And so let's restrict to the following very simple category of singularities where we have y to be c and the function is z to the 8th. And so this category of singularities is rather simple. So it has just finitely many decomposable objects. So there are C and then C Z mod Zi, where I is between 1 and 7. And so everything else is a combination of these decomposable objects, and then by the methods of linear algebra, you can actually compute the spectrum of this category. And it actually consists of the numbers 0, 1, and 3. So the number 2 is not present here. So it's a simple calculation, but still a bit involved. So I can refer you to a paper by Favero, Ballard, and myself, which appeared in November on the internet, where this is done in full detail. So,
9 as well.
Hmm?
Done 9 as well.
Yeah, it's for any n and for any d and e. So.
8 is a variable.
Yeah. So, but this is the first time where I know that this not, I mean, for me at least, this was the revelation that this is the first time I've seen a gap in the spectrum, actually.
Is there some statement about bounds on the spectrum for these singularity categories?
Yes, there is a very precise statement there in this paper about dB sync precisely. And in fact, using Orlov's theorem on the connection between dB sync and dB, you actually get a limit from above on the dB of x. All right, so now let's remember some classical work by Bondel and Orlov on the behavior of derived categories under birational transformation. So, if you have X smooth projective, and we take Y to be a smooth subvariety, then we can consider the derived category of the X blown up in Y. And then this derived category is going to be presented by a semi-orthogonal decomposition of the derived category of X, and then as many copies of derived category of Y as big the codimension of X, of Y in X is minus 1.
So what's the criteria? What is this X has
This,
index 1?
this means X blown up in Y. So I take a smooth blow up with a smooth center in X. So let's say that the codimension, just for simplicity, is equal to 2, then this is what we're going to get. So in any case, that suggests that the spectrum certainly is not an invariant of the birational, under birational transformation. So from what the conjecture says and what this example would suggest is that if we start blowing up, the spectrum actually is going to change drastically due to this semi-orthogonal decompositions. But there is a different type of invariant which is actually a birational invariant, and so I'll save you the all these intermediate steps which can be actually followed and can be found in the paper that I have mentioned, but just formulate the following to a conjecture. That if X is rational, then the gap of dB of X is less or equal than n minus 2. So let me remark here.
What's the number of gaps?
No, I'll say what the number. So the remark I'll say what it is. So gap of dB of X or of any category is the maximum missing interval in the spectrum of tau. So, I mean, in this particular case, the gap is equal to 2. And clearly, we will say that we have a gap of length r, of length s, if A and A plus S are in the spectrum. but anything in between is not.
Surely you should shift this number by 1, right? Because otherwise you're going to have a gap of 1.
Yeah, that's fine. I mean, that's fine. So, all right, so now the statement here is that if I look at the spectrum and I look at the maximal gap, then this gap, in the case of x being rational, is always less or equal to n minus 2. So all these examples, of course, which we have considered for rational manifolds certainly satisfy.
What is n?
I'm sorry, I apologize.
How about P1?
All right. So.
But do you believe there are never gaps for surfaces?
Yes, I'll return to this question. I mean, for meaning complex surfaces. Yeah. All right. So now, but I don't say that if the gap is equal to n minus 2 precisely. So then from here I can conclude that the manifold is rational. So the issue with the gap being equal, so the opposite statement is not the statement that I'm making. It's just a statement in one direction. And so let me just briefly give some examples here. So if I have x to be three-dimensional cubic, generic one, then the spectrum of dB of x conjecturally is 3, 4, 5, and so on. 14 and 15 is missing. So now if this calculation is correct, it needs to be checked, that would give a different proof of the classical result by Clemens and Griffiths, which tells you that the generic three-dimensional cubic, in other words, smooth three-dimensional cubic, is not rational. So indeed the gap is, if x is rational, the gap is going to be 1, and it's 2 in this case.
Can you get all these numbers in the list? Can you get the numbers in the list?
I mean, there is a method, I'll discuss it there, but it's not at the moment rigorous.
But you're saying that this conjecture is known in the case of this, I mean, this new proof would still appeal to this conjecture? Or?
So what I'm saying is that the calculation of the spectrum is not completely rigorous in the moment. If this calculation is made rigorous, then this gives a different proof of the Clemens.
Assuming,
assuming this conjecture. All right, so now, of course, there could be examples where the spectrum is actually still equal to, I mean, there could be three-dimensional examples where the gap of the spectrum is equal to 1, and they are still non-rational manifolds. And so I'll briefly discuss.
I can ask a little bit. I mean,
Yes.
Before you did this calculation, did you already know that you thought there would be a gap at 15?
Did I know what?
Could you already tell before you did this calculation the gap was going to be a 15?
No.
Oh, okay.
But I mean, yeah, you need to do it properly. So there are examples of dimension of x being equal to 3, where this gap is actually equal to 1, and still we have non-rationality, so I'll give you several examples like that. The first one is the classical example by Artin and Mumford. So X is a two-sheeted covering of P3 ramified in a K3 surface with 10 nodes. So in this particular example, the gap of the spectrum of dB of x is equal to 1, but this manifold is already close to 40 years to be non-rational.
So, excuse me, is it double covering?
Yeah.
Then it's singular.
No, the ramification divisor is singular. No, it's not singular.
It's ramified on a nodal.
On the nodal K3.
If ramification divisor is singular, then the double cover is also.
It says threefold double points.
You want to take some resolution, small resolution? Or?
I mean, it says threefold double points. It does 10.
Okay, so sorry about that. So x is defined like that, and I take the result to 1.
Small resolution?
Yes.
And when you say the gap equals 1, does this mean that you can prove there are generators realizing all values in your
That's
conjectural
correct.
range?
Yes. That's correct, yes.
So the gap is 1 if indeed the maximum possible generation time is rank of cohomology plus.
That's correct, yes. And so there are many examples of this behavior. So one of them is the two-sheeted covering of quadric.
There might be.
Ramified in the octic with 20 singular points, and then we take again this resolution. So this is also known to be non-rational, but again the gap of the spectrum of dB of x is equal to 1. And so similar to this, we can consider a two-sheeted covering of P3 ramified in a sextic with 35 singular points. So again, so this is not rational. notation. And so in all of these cases, the gap is actually equal to 1. And the reason for that, at least conjecturally, that I want to suggest is the following. So the derived category of this actually has a semi-orthogonal decomposition, which includes the derived category of an request surface, and then some semi-orthogonal decomposition with some exceptional objects. Similarly here, and here. So this conjecture was checked in some cases, in this particular case by Kuznetsov, and in this case by me and Prerokowski and Tiliev. So now, well, what to do in this case when actually this spectral invariance doesn't allow us to detect rationality. So there is a bit of a deeper invariant which I want to discuss now, and this is so-called Noether-Lefschetz spectrum.
Excuse me, the second example, where it's ramified?
It's in an octic. So you have an octic surface in the quartic in P4, in the quadric in P4, but also you have 20 singular points, so that you kill the intermediate Jacobian.
So these are non-rational because they have the wrong cohomology ring or something?
So in two of the cases they are not rational because H3 has a torsion Z2. And so I forgot what is the in the middle example. I mean, this in these examples, this one and this one, these Z2 precisely come from the fundamental group of the request surface. That is, and in this case, it was all pretty much understood already by Artin and Mumford sometime. All right, so Noether-Lefschetz spectrum. So if we consider a category, we can consider its Hochschild cohomology, and then for every ideal I, this has a ring structure. We define the differential graded category annihilator of I, and this is a DG category, and with this DG category we associate the spectrum of the annihilator of I, but by this I don't mean the spectrum of this DG category by itself. It might not be even triangulated, but what I mean is that these are all generators of tau in annihilator of I. So in other words, what I get is a presheaf over every ideal here.
Excuse me, generators of what?
Of generator of the big category, tau. So I have tau, I take the Hochschild cohomology, this is a ring, it acts on the category. I take an ideal, I consider the annihilator. This is a digi subcategory. And I consider all generators inside here, which generate the big category tau.
Isn't it what generated by? I mean, this generator should be an annihilator, right?
So, I mean, there is a map between the spectrum of the big category and this subset in here. But, it's more shredded, so it's much easier to get a gap for this spectrum than the spectrum of the whole category.
Generator lies in annihilator.
Yes.
Isn't it what it generates also lies in there?
Well, if you like, you can consider you can think of this as a spectrum of the whole subcategory. Yeah. Not just of objects, but of subcategories. You can do that.
He's saying that how can the generator possibly lie in the annihilator if the annihilator is proper? I think that's what he's asking.
I mean, there are many. So if I have an ideal, I mean, the ideal actually annihilates many things. I mean,
Maybe if you give us an example.
yeah, I'll give an example. So in the next talk. So what I wanted to say is that in these three cases, no matter that the spectrum actually is equal to 1, the gaps in the Noether-Lefschetz spectrum of this category is greater or equal to 2. Sorry.
Are we picking an I? What is this spec n now?
So we have all these ideals here, and so for each ideal, I have a spectrum of this DG category, which precisely consists of the generation times of all generators which lie in here. And so I get a presheaf of this form, and so if some of these categories have gap equal to 2 or higher, then this is what we were going to say that.
We're just taking max of spec
That's
and I
correct.
over I.
Mhm.
I don't need a presheaf. I mean, spec and I is just a set of numbers.
Yeah, actually, you can prove that this is a presheaf of this number. But I mean, all right. So if you don't like presheaf. So what I would like to suggest that having a bigger gap here in the Noether-Lefschetz spectrum, actually, this gap of Noether-Lefschetz spectrum being bigger than 2 is actually also an invariant related to the birational geometry, but this is to be checked. And so let me just finish with the example that I have started with, namely this one here. So if I have X to be a generic 4-dimensional cubic, then conjecturally the spectrum of dBFX is the sequence of numbers. So therefore, if these conjectures are correct, then we conclude that generic four-dimensional cubic is going to be non-rational. But of course, there are examples of smooth four-dimensional cubics which are known to be rational, like Pfaffian ones. And so basically what we have is that, so we have the moduli space of four-dimensional cubics, and then here inside we have different Noether-Lefschetz components. And so for this Noether-Lefschetz component, we know that there is additional class in H22 which appears, but also generalization of the work of Borchers tells you that this moduli space of four-dimensional cubics has an automorphic form associated with it. And basically, there is the following connection between the following three subsets. So the Noether-Lefschetz loci are in 1-1 correspondence with these Higner divisors for this automorphic form. And with a set of gap drops. Namely, we move from this behavior of the spectrum to this one. So the gap drops from 3 to 2. And so I don't claim that in this set where the gap drops, I know what's happening with rationality, but it's certainly not generic behavior of the
this last statement is a theorem?
No. So this is a theorem, and this is a theorem. So sorry, this is a theorem. This is a theorem. Or this is a little bit.
This is the gap or the Noether-Lefschetz gap?
Just the gap. So
you didn't tell us why you called that a Noether-Lefschetz gap.
No,
Sorry, if those two are theorems, then the third one should be theorem 2.
A little, if you know the gaps occur in other Lefschetz loci, then you know that
say it again.
gap drop means what? The gap's getting bigger.
Gap's getting smaller.
So if,
I think the left-hand arrow presumably is a theorem subject to the computations being correct.
yeah,
So it's a sort
That
of
is
conjecture with evidence.
yeah, that's correct. Yes. So in a way, up to the calculation of P2 and P3, these are solid results. Everything else is a conjecture at the moment.
Any questions?
Yes.
What's the source for the gap?
What
What's the
is
reason
it?
for the gap?
Why they are gapped? Okay. So I mean, the whole second lecture will be dedicated to that. But in short, it's a certain monodromy phenomena on the Randall-Ginzburg model.
I was confused by this use of the word Noether-Lefschetz.
Yes.
Over here.
Mm-hmm.
Did you tell us what this had to do? I mean, over here you weren't discussing Noether-Lefschetz.
No, so this is not. I mean,
These are the same Noether.
so this is classical Noether-Lefschetz loci.
Yeah.
And so this is the Noether Lefschetz for where instead of the modular space, I just consider the vector space, or if you like, the ring of the Hochschild cohomology. And then, so the ideals play the role of the Noether Lefschetz loci there. And over certain ideals, actually, the gap could drop or jump depending what the behavior is. So that's why, okay. So for me, these ideals are the analogy of the Noether Lefschetz loci in the classical situation.
But, so the Noether Lefschetz gaps play no role in this?
Actually, they most likely are connected, but I haven't been able to establish this connection completely.
Katzarkov spectrum. The name at the moment is
Is there a reference for the automorphic form stuff?
Yeah, so this is joined with Iliev and Scheiringer, and probably will be posted relatively soon.
Any other questions? If not, then we thank Ludmil again, and we'll be back here at 2.